Hello everyone. In this video, we are going to talk about classification models. So we are going to switch gears and talk about stuff that is a little different than what we have done so far. This is a reading list. There's a whole chapter on different kinds of classical classification models in this text, but we are only going to focus on logistic regressions. However, I would definitely encourage you to read the rest of the chapter as well. It's very informative, and if you would like to know about other types of classification models, this text and this chapter is a very good place to start. So let's begin. Uh, so the way it works is that in statistics and data science, we often counter problems where we are trying to predict outcomes that fall into categories rather than continuous values. Think about these everyday examples. You might want to predict whether a person has a disease. That is a yes or no outcome. Or you're trying to build a spam filter that needs to classify emails as either spam or not spam. Financial institutions constantly need to assess whether a customer will default on a loan. Schools might want to predict if a student will pass or fail an exam. These are all classification problems where the outcome is not a number on a scale, but rather a discrete category. The thing is, these types of outcomes require specialized models designed specifically for categorical data. We can't just apply our standard linear regression models designed in these situations because we need something different that can properly handle these yes or no type of questions. And this is where classification model comes in. Now, you might be wondering, why can't we just use a linear regression for these binary outcomes? After all, we could just code yes as 1 and no as 0, right? Well, linear regression has some fundamental problems when applied to binary outcomes. Remember that a linear regression model looks like y equals beta naught plus beta 1 x1 plus beta 2 x2 dot 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 up to epsilon. This works great for continuous outcomes, but breaks down when it comes to binary data. The first major issue is that linear regressions can make predictions outside of the 0-1 range. If we are modeling probabilities, getting predictions like negative 0.3 or 1.5 doesn't make any sense because probability has to be between 0 and 1. Another problem is heteroscedasticity. That's a fancy way of saying the error variance isn't constant across observations. With binary data, variance structure is inherently different than what a linear regression assumes. We can also have non-normal error distribution with binary data. Linear regression assumes normally distributed errors, which simply isn't the case when your outcome is binary. Finally, linear regression assumes that the effect of predictors is, well, linear. But the relationship between predictors and probability of binary outcome is rarely linear in practice. It's usually S-shaped, where the linear regression is just not able to capture appropriately. So let's visualize what I just said. This graph really shows us the heart of what the problem is when we use linear regression for binary outcomes. Look at the actual data points. They are either at 0 or 1 on the y-axis because we have a binary outcome. Now follow the red line, which represents what a linear regression would predict, and see how it goes below 0 and above 1. These predictions make no sense because what we are dealing with over here is probability and it cannot be negative or exceed 1. The blue curve, on the other hand, represents what logistic regression would predict. Notice how it elegantly curves and always stays within the 0-1 range. That's exactly what we want when we are modeling probabilities. This S-shaped curve makes intuitive sense too. When our predictor variable is very low, the probability should approach 0 but never quite reach it. Similarly, when the predictor is very high, the probability approaches 1 but doesn't quite exceed it as well. This is why logistic regression is so valuable for binary outcomes. It naturally constrains predictions to valid probability values and models a relationship in a way that matches what we actually observe in the real world data. So we have seen that linear regression has this fundamental problem when dealing with binary outcomes. It can predict values less than 0 or greater than 1, but these predictions don't make any sense when we are talking about probability. Probability, by definition, must be between 0 and 1. You can't have negative values or a value greater than 100% because it is not right conceptually. What we really need is a model that naturally constrains our predictions on to this valid probability range from 0 to 1. We need something that, no matter what the value of our predictors take, will always give us a sensible probability estimate. This is the core functional form problem we are trying to solve with classification models, and it leads us directly to why we need specialized approaches for these scenarios. And this is where classification models come in handy. They specifically are designed to handle categorical outcomes, like the ones we have been talking about. These models offer several key benefits over trying to use a linear regression for binary data. First, and most importantly, they naturally constrain predictions to that valid probability range between 0 and 1 that we just talked about. So we essentially rule out any nonsensical probability estimates. They are also built to model nonlinear relationships appropriately. Remember the S-shaped curve that we saw? Classification models can capture the natural S-shaped relationship between predictors and the probability outcomes. On top of that, these models provide meaningful interpretations for binary outcomes. We can talk about odds and probabilities in a way that make intuitive sense for yes/no questions. And finally, they have better statistical properties for inference, which makes our analysis much more reliable. These are some of the several common approaches to the classification problems. We are only going to talk about logistic regression, but we also have in our toolkit probate regressions, which are very similar to logistic. We also have discriminant analysis as well as generative models for classifications. But in this video and in this course, we are going to talk only about logistic regression. So let's get into the specifics of logistic regression. At its core, logistic regression is a statistical method specifically designed for analyzing binary dependent variables, those yes/no outcomes that we have been discussing. When it comes to model the probability that an observation belongs to, so what it models is a probability that an observation belongs to a particular category. So instead of predicting a continuous value, like in a linear regression, we are predicting the probability of an event occurring or an observation belonging to a particular class. The name logistic regression comes from the logistic function that is used to transform linear predictions into probability values. We will look at this function in detail in just a moment. One of the reasons logistic regression is so popular is its widespread use across several fields. You'll find its application in medicine for diagnosing diseases, in economics for predicting consumer choices, through our social sciences for modeling behavior, and extensively in machine learning for all sorts of classification tasks. It really is a fundamental technique in computational statistics, and understanding it well will give you a solid foundation for more advanced methods later on. Now let's look at the heart of logistic regression, which is a logistic function, sometimes called the sigmoid function. This is really the key mathematical innovation that makes logistic regression work. The formula is sigma z equals 1 upon 1 plus e to the power negative z, where e is the base of the natural logarithm. Don't have to remember the formula. The important thing here is to understand what it does. This function maps any real number onto a value between 0 and 1, which is exactly what we need for probability. If you plot it, you get this beautiful S-shaped curve that you can see in the figures. And you can take a look at the behavior as well. As z approaches negative infinity, the function approaches 0, but it never quite touches it. And as z approaches positive infinity, the function approaches 1 but never exceeds it. And this perfectly captures the behavior that we want for our probability predictions. The graph on the right shows us how changing the parameters affect the curve. Look at the middle graph where we change the slope parameter b1. By changing that, we make the curve steeper or flatter. A steeper curve means probability changes more dramatically around a threshold point. In the bottom graph, we see changing the intercept parameter b0 that shifts the parameter left or right. This determines whether the probability crosses any threshold. The parameters give us flexibility to model different kinds of relationships between our predictors and the probability of an outcome, which while always keeping our predictions within a valid probability range. So let's now look at the basic structure of a logistic function. The structure has three key steps. First, we start with what's called a linear predictor. This looks very similar to what we use in the linear regression. We have our intercept beta naught plus sum of our predictor variables, each multiplied by the respective coefficients. So beta 1 plus x1 plus beta 2 x2 up to beta p xp. We can call this the combined value of z. Second, and this is the critical difference from linear regression, we apply the logistic function to transform this linear predictor onto a probability scale. We take that z value and plug it into the logistic function probability y equals 1 given x equals 1 by 1 plus e to the power negative c. And this transformation ensures that the probability is always bounded by 0 and 1. It's like having the best of both worlds. We get to use a linear model on the inside while ensuring that our outputs make sense as probabilities on the outside. To really understand how to interpret logistic regression, we need to talk about odds and log odds. Let's say the probability of an event occurring is pi. That is, probability y equals 1 given x is equal to pi. The odds of that event are defined by pi divided by 1 minus pi. This is the ratio of success to failure, or in betting terms, it's like saying the odds are 3:1, meaning 3 successes for every 1 failure. Taking this a step further, the log odds, or also called the logit, is the natural logarithm of the log of the odds, ln pi divided by 1 minus pi. And this is where things get interesting. When we work out the math, it turns out that this logit exactly equals our linear predictor. So log of pi by 1 minus pi equals beta naught plus beta 1 x1 plus beta 2 x2 up to beta p xp. This is really important because it means that we can interpret our coefficient in terms of log odds. While the relationship between our predictors and the probability is non-linear, that is that S-shaped curve, the relationship between our predictors and the log odds is perfectly linear. And this gives us a clean way of interpreting the model that we will discuss more in just a bit. So when it comes to estimating the parameters, we can't use OLS like we do in linear regressions. OLS works by minimizing the sum of squared residuals, but this approach doesn't work well with binary outcomes. Instead, we use a method called the maximum likelihood estimation, or MLE. The basic idea is that we find the parameter values that make our observed data most likely to have occurred. Mathematically, we are trying to maximize the likelihood function shown on the slide as L of beta, which is a product of I to n pi raised to the power yi times 1 minus pi raised to the power 1 minus yi. This looks complicated, but it essentially is calculating the joint probability of observing all our data points given our model parameters. Unlike the linear regression, there is no closed form solution to this. We can't just write down a formula and get our answer. Instead, we need iterative numerical methods to find the parameter values that maximizes the likelihood function. The computer basically makes an educated guess, evaluates how good that guess is, and then refines it until it converges on the best values. That's why you will always need a software to fit logistic regression models. The math is too complex to do by hand, but luckily for us, we have computers like statistical softwares to do this calculation for us. Like any statistical model, logistic regression has certain assumptions that we need to take into account. First, we need a binary dependent variable, which is kind of obvious because if you're using ordinal logistic regression, and ordinal because that's what we need. This is the fundamental design. We also assume that observations are independent of each other. This is important for statistical validity of our results. Another key assumption is little or no multiple linearity among predictors. Highly correlated predictors can cause estimation problems and make interpretation difficult. We do assume that there is a linear relationship between our independent variables and the log odds of the outcome. Remember, it's not linear with the probability itself, but with the log odds. The sample size is important too. A rule of thumb is that you should have at least 10 events per predictor variable. With too few observations, our estimates become unstable. And we should watch out for influential outliers that might skew our results. But here's the nice thing. Unlike linear regression, it doesn't assume normal distribution of errors or homoscedasticity. Doesn't assume a linear relationship between the independent variables itself. These relaxed assumptions make logistic regressions more appropriate for binary outcomes, where these conditions typically wouldn't hold anyway. There are three main ways we can interpret coefficients. First is we have the log odds interpretation. So if we have a coefficient beta1 for variable x1, we can say that 1 unit increase in x1 is associated with beta1 increase in the log odds of success. But then, to be honest, log odds is not very intuitive, which is why we often use our second approach, which is the odds ratio. What we do over here is that we raise this coefficient exponentially to the power of our coefficient, giving us an e to the power beta1. This tells us that 1 unit increase in x1 multiplies the odds of a factor of e to the power beta1. For example, if e to the power beta1 equals 2, then increasing x1 by 1 unit doubles the odds of success. If it is 0.5, it halves the odds. It's easier to relate to odds than log odds. Finally, we have the probability interpretation, which is the most intuitive but also most complex. The effect on probability depends on where you're starting from. This is because of that S-shaped curve that we saw earlier. The largest effect occurs where the probability is around 0.5, and the effect gets smaller and smaller as you approach either 0 or 1. So the same change in predictor can have different effects on the probability depending on the value of all the other predictors. Once we have built our logistic regression model, we need to evaluate how good it is. There are several approaches to this. For significance testing, we can use the Wald test for individual coefficients to see if each predictor has a statistically significant effect. We can also use the likelihood ratio test to compare nested models and see if adding variables improve the model significantly. For classification performance, we use several metrics. The accuracy measures the overall proportion of correct predictions. Precision tells us what proportion of our positive predictions were actually positive. Recall or sensitivity tells us what proportion of actual positives were correctly identified. And the F1 score combines precision and recall into a single metric. We can also use an ROC curve and calculate the area under the ROC, which we call the AUC, to evaluate the model's discriminative ability across different threshold settings. And the confusion matrix gives us a comprehensive view of the true positive, true negative, and false negatives. For goodness of test, we have several measures to work with, but the most common measure of model evaluation is the pseudo R-squared, which we will cover in more details in the next few slides. These are just attempts to create an analog version of the R-squared from linear regression. So in linear regression, we have this very intuitive measure called R-squared that tells us the proportion of variance explained by the model. And the formula is 1 minus SSE by SST. But with logistic regression, we run into several issues that makes this approach problematic. First, logistic regression uses MLE, not OLS. The math framework is different. Second, there is no direct equivalent to error variance in logistic regressions. The concept just doesn't translate directly. Third, binary outcomes don't really have the same concept of variance explained that continuous outcomes do. When your outcome is either 0 or 1, thinking about variance becomes tricky. And because of these issues, we need alternative measures for goodness of fit in logistic regression. That's where pseudo R-square comes in. They are called pseudo because they are attempting to serve a similar purpose to R-square in linear regression, but they are calculated differently and have somewhat different implementations and interpretations. To understand pseudo R-squared, let's think about what a regular R-squared does. It asks the question, how much better is our model than just predicting the mean for everyone? Pseudo R-squared asks a similar question. It asks, how much better is our model than a null model? In a logistic regression, a null model predicts the same probability for all observations, usually the overall proportion of success in the dataset. Pseudo R-squared measures compare the likelihood of our fitted model to that model, which is the simplest one. But it's important to understand that they are not directly measures of variance explained like regular R-squared. Think of them as answering the question, how much have we improved our predictions by including these predictors compared to not using them at all? That's a useful question, even if it's not exactly the same as asking about variance explained. And these are the three common measures of pseudo R-squared. First we have the McFadden's R-squared, which is probably the most commonly used measure. This formula is 1 minus log of L fitted by log of L null. Essentially, it's comparing the log likelihood of our fitted model to the log likelihood of the null model. Closer this ratio is to 1, the better it is performing. There are a couple of other measures, Cox and Snell and Nagelkerke R-square. These are just modifications, especially Nagelkerke R-square is a modified version of Cox and Snell, but the math is different, but the objective in this is the same. In all these formulas, L fitted is the likelihood of our fitted model. L null is the likelihood of the null model, and N is the sample size. The key idea is that we are comparing how much more likely our data is under our model compared to the simplest possible model. All pseudo R-squared measures range from 0 to 1, with 0 meaning our model is no better than the null model, and 1 meaning we have perfect prediction. But in practice, you almost never see values close to 1. Close to 1. One of the most important things to understand is that typical values of pseudo R-squared are usually much lower than what you would expect from linear regression R-squared. Like if you're used to seeing R-square of 0.7, 0.8, you can kiss those expectations goodbye, because it's very, very unlikely that you will see such a number when it comes to pseudo R-squared. Usually, a number ranging from 0.2 to 0.4 are often considered excellent. In fact, McFadden himself, when he was developing the statistic, he suggested that 0.2 to 0.4 indicates a very well-fitted model. And also, it's worth noting that pseudo R-squared measures are generally better for comparing models than for assessing absolute goodness of fit. These are most useful when you're trying to decide between different models for the same data, rather than making a judgment on how good a single model is in isolation. So let's directly compare the regular R-square from linear regression with pseudo R-square from logistic regression. Regular R-squared is based on the sum of squared residuals. It has a very direct interpretation as a proportion of variance in the dependent variable that is explained by the model. We typically see higher values in practice, like something like a 0.7 or higher, when that we consider as a strong model fit. Like pseudo R-squared, regular R-squared increases with every predictor you add to the model. It can lead to overfitting if you're not careful. But we do have adjusted R-squared in linear regression, which penalizes for the number of predictors to help address this issue. In contrast, pseudo R-squared measures are based on likelihood ratios. They are a more indirect interpretation. They are telling us about the improvement over a null model rather than about the variance explained. As mentioned, the values are typically much lower. Somewhere around 0.2 to 0.4 is considered very good. Pseudo R-squared also increases with every added predictor and can lead to overfitting. And we have multiple versions of different properties, which can sometimes give us different results for the same model. Understanding these differences is crucial when you are evaluating logistic regression models, especially if you are already familiar with linear regressions. To make this more concrete, we have a model predicting consumer purchase behavior, and we calculate the McFadden R-square of 0.25. How do we interpret this? We could say that our model explains about 25% of the improvement from the null model to a theoretically perfect model. It's not saying that we are explaining 25% of the variance in the traditional sense. Those concepts don't apply here. Now, if we add another predictor to our model, the R-square increases to 0.27. So that only means a small improvement of 0.2. We need to ask ourselves, is this additional complexity worth such a modest gain in predictive power? Often the answer might be no, especially if we value the model for simplicity and interpretability. The figure on the right shows an interesting comparison of R-square values for linear regression and McFadden pseudo R-square for logistic regression if we add more predictors. Note that the R-square is consistently higher than the logistic regression's pseudo R-square. And this is exactly what we would expect based on our discussion. And also note that both curves flatten out after 4 or 5 predictors. This suggests that additional predictors beyond this point aren't adding much value, a common situation in many modeling scenarios. This is why these measures are so useful for comparing different models' specifications. So, to wrap up, remember pseudo R-squared measures are approximations of explained variances. They are trying to give us something analogous to R-squared, but they have their limitations. Their primary value is for comparing models on the same data set. So if you're trying to decide on which model to use, comparing pseudo R square can help you in that decision. You should not expect pseudo R square with very high numbers. And while McFadden's R square is the most commonly used, it can be helpful to consider multiple measures for consistency. So that's kind of this chapter in a nutshell. I hope this was useful, and if you have any questions, please do not hesitate to let me know.